Reliable power is critical in industrial, telecom, automotive, and data center systems, especially when you're stepping up to 48 volts or even 100 volts. Hi, I'm Ricky Flores, engineer here at Mouser. Welcome to Engineering Bench Talk, where we show you how to get started with the latest tech from our manufacturing partners. Today we're hands-on with the eVault LTC7892BZ, an evaluation board built around Analog Devices LTC7892, a high-efficiency, high-voltage boost controller ideal for demanding power systems. We'll set it up, run live measurements, and test how it handles ripple, transients, and real-world loads. The eVault LTC7892BZ runs at 500 kHz and outputs 48 volts with up to 98% efficiency. But if you want a different output voltage, just change the values of R18 and R19. Unlike other controllers, the LTC7892 handles gate driving and protection internally, supports up to 3 MHz switching, and it's compatible with a wide range of gallium nitride and logic level MOSFETs. Now let's get hands-on. We'll start by setting your bench supply to 9 volts, but leave it off for now. That's the minimum input voltage for this board, but it can easily be adjusted by changing the values of R62 and R63. Now connect VIN to the positive terminal, ground to negative, and use low resistance cables that can handle a few amps. Use a multimeter across Vout to verify the 40 volt output, and this part's critical. Make sure both run 1 and run 2 jumpers are set to on. If either one is off, the controller stays disabled, since they are linked through a 0 ohm resistor at R64. Please note that boost controllers can misbehave if VIN ramps too slowly. Crossing UVLO, which is around 5 volts, gradually can cause erratic gate drive and stress capacitors or switching elements, and potentially damage your board like in this case. With no load, the output gives us clean 48 volts. Next, let's measure the ripple output voltage. Set your oscilloscope to AC coupling, 20 MHz bandwidth, and use a short ground spring or tip adapter to reduce noise. At VIN of 24 volts, ripple with no load is about 860 millivolts. Next, add a 1 amp load and the ripple jumps to 1 volt. This noisy waveform is expected due to switching artifacts, layout effects, and probe setup. These values match what's shown in the datasheet, which is around 900 millivolts peak-to-peak in burst mode with I/out of about 10 milliamps. Burst mode improves light load efficiency but increases ripple and low-frequency noise. In continuous mode, ripple smooths out. In our case, we saw about 171 millivolts peak-to-peak at no load, and about 192 millivolts peak-to-peak at 1 amp. Let's now apply a 0.5 amps load at the output. Here you can see that the voltage holds steady at 48 volts. But be careful, cable resistance matters. Just 0.5 ohms in your wire at high current can drop your input voltage several volts, which may cause regulation failure or even shut down. Next, we'll do a dynamic load test and continuous mode. For this, make sure you change the P1 jumpers as shown. We'll program a 2-step list. Step 1 at 0 amps, Step 2 at 2.5 amps, set the slew rate at 2 amps per microsecond. The dwell time is set to 1.5 seconds and set the number of repeats to 25 times. so that we can have enough time to capture our transients. Next, let's set our oscilloscope. Channel 1 connects to Vout, select AC coupling, and a 20 MHz bandwidth. Channel 2 will be our current monitor, which is connected to the back of our programmable load, set it to DC coupling, and also choose a 20 MHz bandwidth. Now run the load program, and you will see the transient response. In our results, we see a fast recovery, tight regulation, and minimal overshoot, exactly what you will expect from a well-tuned gallium nitride boost converter. You can add a higher load if your power supply allows. Just make sure the heatsink is mounted properly. Even without it, thermal performance is solid, as shown here, thanks to the 6-layer PCB design of this development board and thick copper planes. We tested power efficiency at VN values of 24 volts and 36 volts with a 2-amp load. Our results align with the datasheet, showing around 97% efficiency. Pretty impressive for a high voltage, high power boost stage. To wrap it up, the LTC7892 delivers clean, efficient, and scalable boost conversion. The eVault LTC7892BC makes it easy to prototype high voltage systems with great ripple and transient performance. Need something more compact? The LTC7893 offers a single output alternative with the same 100 volt capability, only in a footprint that's 44% smaller than the LTC7892. You can find evaluation boards for both boost controllers and Mouser.com. Links and full descriptions are in the description below. Thanks for watching. Don't forget to like, subscribe, and follow us for more bench talk videos.